So tonight we're going to talk about number sense in Singapore math. We're going to talk about how we end up at a lot more at the math that we're used to, stacking two numbers on top of each other and adding them. We still do that in Singapore math because it's the most efficient and effective way to get an answer. That's why we all learned it. But it's important that we know what we're doing when we do that. That's where the conceptual basis of Singaporean number sense comes in. We'll talk about mental math strategies and how Singapore teaches those. And then kind of some go-to phrases at the end for, as a parent, what are some things you can say to just help the kid get unstuck? And that's what we're going to take a look at. So the Singapore approach, the entire program is based on this kind of instructional idea that we start with things in the concrete, whether it's adding or subtracting or we're talking about geometry. We actually start with something we can touch and manipulate and work around with and see. And then work towards a kind of a pictorial or efficient drawing of what that is and what that looks like, and then eventually move into the abstract. So this is where a lot of us spend most of our math careers, and we know that we're eventually getting there, like I said, because it's efficient and it's good. It gets you the right answer. The problem is we know that if that's all we're doing, our only options, if a kid doesn't see that 2 plus 1 equals 3, then what do? Tell them again, and then ask them to repeat it back, and tell them again, and ask them to repeat it back. And that creates a problem, really. It creates a struggle for kids who struggle with math. It also creates a lot of people who hate math, which is also very popular among people who learn math this way, right? If you didn't get it, you were told again, and then told again, and then told again, and so we have, really in the country, people who are good at math and people who are not, because that's how kind of we were taught. So we're trying to develop the conceptual and have a place to go with kids if and when they don't get this at certain times. So that's reinforced in the textbook over and over and over again. As you can see here, this is a word problem about Will buying 24 eggs and then breaking 7 eggs. And in first grade, it started out modeling with blocks. Let's get 24 blocks, and then let's take 7 away and count them up. And this is bar modeling, which our next session in 2 weeks is going to be all about, where that's really an efficient way to draw 7, is draw a bar and calling it 7, drawing a bar and calling it 24. And then we end up at the, if you can see that, it's really small. It's just 24 minus 7 equals 17. So that's that. That's actually a snapshot of a page from the textbook. That concrete to pictorial to abstract is reinforced kind of on a daily basis in the instruction. So what is number sense? Number sense is like common sense for numbers. And it's what we are desperately trying to instill in kids when we teach them math. Not just how to be an algorithm robot and hammer through that, but how to think with numbers and be fluid in their thinking with numbers, and how to have good number sense. We know that students with strong number sense do the following things. They can compose and decompose numbers. They can understand the relationship between numbers. They can understand patterns and the number system, that's what math is, right? It's the science of studying patterns and systems. And they understand operations. Not only are they able to add, subtract, multiply, and divide, but they know what adding is, and they know what subtracting is. You'd be amazed, I think, at how often I remind a 6th grader or 7th grader who's struggling for a word problem that subtraction is takeaway. That's the old kindergarten thing, and somehow when they get really good at subtracting, they lose that idea somewhere along the line. And they're like, what do you want to do? I want to take that away. Well, how do you do that? I don't know. This is subtract. So we'll start with composing and decomposing numbers. So in kindergarten, most of the kindergarten year is with, hi, come on in. That's all right. Composing and decomposing numbers. So again, we start with the concrete, and we say that 4 looks like this. Okay, it can be represented like this, but here's where we start. This is 4, right? Too often we start here, but this is 4. Well, 4 is also this, 2 and 2, and 4 is also 3 and 1, and all those things can be 4. So at the beginning of the kindergarten Singapore curriculum, there's like a week on each number up until 10, and they just play games and draw pictures with and count stories that all add up to like the number for the week. It's all about composing and decomposing numbers. And then we get into a little bit more abstract. This would probably be more of that pictorial, right? It's the efficient way to show that. Here's 5. How many different ways could you make 5 with blue and yellow? It could be 5 and 0, 4 and 1, 3 and 2, composing and decomposing numbers. And then they do get to the abstract of actually representing that with numbers. more reinforcement of the concrete to pictorial to abstract. Here they have pictures of the things that they're used to playing with in class and working with in class. The things you have in front of you are 10 frames. In kindergarten, we start with a 5 frame, which is just 5 things. And this is from an early age structuring kids in the idea of the pattern of base 10, which our entire number system is based on. And just composing, decomposing numbers. We tell stories, count how many, always something that you can touch and look at. Then a month later in kindergarten, we're above 10, and we're seeing that 12 is 10 and 2, and so on and so on. Then we get into a really efficient strategy for decomposing and composing numbers. It's called a number bond. Many of you, maybe in the early grades, have kind of seen this in homework. And the entire idea of a number bond is that any number can be broken apart into 2 pieces, and it can be broken apart in, once we get up into by second grade into the hundreds, it can be broken up into an amazing amount of combinations of ways. But it's that should look familiar to you. All about composing and decomposing numbers. So homework can look like this, and this is the part where I have to sympathize with you a little bit, as a lot of times this is, and maybe the reason why you're here is because this is what we end up seeing at home, right? And we're like, what? Whatever happened to adding 2 numbers? What are we doing here? And so hopefully, again, tonight will be a little bit more of just the context of why you're seeing these things at home. And again, I'll stress, again, it's really okay, and I've cleared with every teacher in the building, that if your kid's not doing this independently, I'll give you some tools for, hey, how could you break apart 5 would be a great thing to ask here. But if beyond that, we don't want you or need you to reteach the entire lesson to them, initialing it, quick email to the teacher, a note on the homework, they couldn't do it. They're not independent with it yet. It's really good information for us as teachers. I don't anticipate any parents in this entire building intentionally trying to get their kid out of homework throughout the year such that it would be a problem, right? We're in this together, we trust you guys, and so write something on it. They couldn't do it, and that's really good information for us as teachers. But does this make a little bit more sense now if it confused you at one point when it came home with homework? Good. We also start, this is my little tiny plug for this math balance, which is just one of the greatest things I've ever seen in the early grades, kindergarten and first grade, where really here I've got a 4 and a 3 that's balancing with a 7. And there's a game we play sometimes in kindergarten and first grade where I hang 2 things. I'll hang the 7 and the 4 on the balance and give the kid 1 more and say, make it balance. And what are they doing there? They're doing algebra, right? 4 plus x equals 7. And so we're one of the other really good parts about this program is we're starting algebraic thinking and pattern thinking from a really, really early age. And they love it. I think it's fun. And we never call it algebra. Until 5th grade. But it's a fun game. It's a cool one. So why are we doing all this stuff? So if you are in the first grade, kindergarten, second grade area, some of this maybe would look familiar to you. And even if it made sense while you saw it, I bet you've asked this question, and a lot of teachers and parents and kids ask this question, why? Why are we doing this? So my hope now is to give you a glimpse into the upper grades, 4th, 5th grade area, 3rd, 4th, 5th grade, and what the kids are able to do when they can compose and decompose numbers. Why do we spend a week on the number 4 in kindergarten? So my goal here is to show you why we do this. We know that when kids can fluidly understand and compose and decompose numbers, that they can apply that skill. Here's our lesson on fact families, which happens in 1st grade. And really, this number bond, once the kids are good and comfortable with that, can answer all of these questions. They can all represent this situation, right? And they can answer how many balls of wool are yellow, how many balls of wool are blue, how many balls of wool are there in all? Are there 3 different questions in word problems? We know word problems are one of the toughest things, especially in the later grades. And the more comfortable kids are with their mental math and their understanding of composing and decomposing numbers, we see that it's all connected. And another plug for the bar modeling is the other great part of Singapore, and that's coming up in 2 weeks. We're doing another night like this about the bar modeling strategy. So again, composing and decomposing numbers. Another reason we do it is to teach addition and subtraction, really, by composing and decomposing numbers. Because when you're adding, so let's see, this is how we first teach addition. Gus has 8 cherries, and Ava gives him 6 more. 8 plus 6. And we know the traditional algorithm of stacking 2 numbers on each other doesn't help here, because if you stack an 8 and a 6 on top of each other, you still have to add them, right? This is the very beginning of those things. So one of the ways they teach it is to make 10. Hi. Make 10, that's okay. Make 10, and then how many more? So when we combine 8 and 6, if I'm really comfortable with the fact that 6 can be broken up as 6 and 0, 5 and 1, 4 and 2, I see that there's 2 more to make that 10. We talk a ton in first grade and kindergarten about how 10 is the basis. So when add means put together, I'm going to toss 2 over there and make 10, and 4 more makes 14. And the algorithm doesn't get at that. That's all about number sense. And again, for many kids, when we all were learning math, you got that and you were good. And if you didn't, what'd you do? You were told again. And so it gives a kid something to do. So at home, this is one of the tools I use most in my math groups. If you have a kid who's struggling with these sort of basic facts, grab 14 Jolly Ranchers and put 6 in M&Ms, pennies, little tiny cubes, and say, show me. I don't know what it is. Can you show me? And that's the language a lot they're hearing in class. And with these tools, it organizes their thinking into base 10. It's not just a bunch of stuff on the table. And that can be a really valuable tool for kids at the beginning. Here's where we start bringing that into the abstract, where instead of actually seeing the cherries go onto the, and make the 10, we would hopefully go that they're understanding the concept, where why are we breaking apart the 6 into 2 and 4? Couldn't it be broken up into something else? Definitely could. But 2 is the thing that's going to make the 10, and the 4 more is 14. So one of the most common mistakes I see in this lesson in first grade is when the kid who loves number, they all love number bounds. They really enjoy doing it. It's kind of fun. But they'll put 5 in 1. And having a conversation about how, is that a correct number bound? Yeah. Is that going to make 10 for you? No, it's not. So trust the nose. Or let them put the 1 on, and then maybe break the 5 into 1 and 4 and get that last one on. Yeah, that's what that's about. Again, more games and counters that show 9 and 3. Give that 1 to make 10, and then 2 more is 12. Take a look. This is amazing to see in a first grade textbook. Not that we force the kids to do that or know that or understand that, but that's a pretty good stuff.
I'm sorry to interrupt,
No, it's okay.
but there is a silver car 4-door down by the playground equipment on the west side of the street with the lights on. Anybody's? Okay.
Must be down with the
One of the other rooms.
Thank you. So here's where we're moving more towards the abstract. Another one of those things we see on the homework and go, what are we doing here? What's going on? What we're trying to do is break the number bond apart to something that will make 10 and make it easier. Any ideas what we break this guy up into? 1 and 4, and this one? 2 and 5. That's not the only thing you could break it up into, but it's the thing that'll make 10 and make it easier. So again, here we tie it back into the concrete, and any sort of tools having these kids count is a big thing to do. Any questions at this point? Super. Let's see. Now we're just bumping up the numbers a little bit. This is an addition strategy. When we do 16 plus 3, again, stacking them on top of each other, you still kind of got to do it. It doesn't really help until we start regrouping. And so the fact that 10 can be broken, or 16 can be broken apart in 10 and 6, we talk about how the 10's wonderful. It's great. We love 10. Don't touch it. Where are you going to give the 3 to? Give to the 6 and make it 9, and then toss it back into the 10. So another phrase I use a lot in math groups would be whether we want to take something away from a 10 or give it to a 10. We don't touch the 10. We love 10. Every time we see a 10, we want to keep it. Don't touch it.
And we know that it's 19 just because we've memorized it.
Exactly. And I'll tell you, it's really...
It feels like it's an extra step.
Exactly.
Because we've memorized it.
Yes. And I'll tell you, there are kids who, without diagnosed learning needs, who have a really hard time with 16 plus 3. They do. And there's especially a lot of kids, the 8 and 6 is a much more difficult one. Okay? And there are kids who are doing this for a really, really long time. And that's okay. Some kids get really fast at it, and then they just know it, and then they're good. And there are many kids who are doing this for a really, really long time. So what Singapore's trying to do is give them an efficient and effective strategy to get beyond that. And we explicitly teach it to them.
So if they're coming up with the right answer by themselves, we should be reinforcing. When we hear them go 16, 17, 19, oh, 19, good. We should be saying, time out, let's go back and let's talk about.
It really depends. I would say specifically with that one, no. Because going up 3 is quick and easy. If they're still doing that with 17 plus 8, 18, 19, 20, yes, at that point we want to get a more efficient strategy in there. Does that make sense?
Yes.
I'm going to skip through the next couple. Here, I want to get to subtraction. So, Ray has 17 cars, and he gives away 3 toy cars. How many cars does he have left? So here's where we're at, don't break the 10 if you don't have to. 17 can be broken up into 10 and 7. And where do we want to take those 3 from? Not from the 10, don't touch it. We'll take them from the 3. And when we take them away, we're just going to have 4 left, and the 10 is 14. Here, we have to break our rule. Sean makes 12 stars and gives 7 to Gina. So we see something that looks like this. And we break our 12 up into 2 and 10. So we don't want to touch the 10 if we don't have to. Where are we going to take those 7 away from? We can take them away from the 10 and we'll be left with 3. And then the 2 are still there, so it's 5. Okay? This isn't the only good strategy here. I see a lot of kids who are still good at this decomposing numbers who would take the 2 away and then take 5 more and get 5. There are lots of good ways to do it, but the one way that is good to start with, but we want to try and avoid, or at least get better at, is 12, 11, 10, 9, 8. That takes a long time, and it's cumbersome, and the kids they miss a number, and they're off by 1 very, very often.
Is stacking at this point?
Uh,
Like if they know how to stack?
Awesome question. I anticipated that.
Sorry.
Thank you for asking. So what about the old-fashioned way here? This is a really, really good question, because many of us would do this. So let's see what actually happens when you do this. 7 away from 2, you can't do it, so you're going to borrow from the 10, cross it out, 12 minus 7, right? And I see kids do this all the time. And then they go to this, and that's okay. We don't want to stop them from doing that or something. One thing I want to communicate to you is we want to try and give them a better option, a more efficient option, and help them practice that. Here we're dividing into equal groups. So when we're composing and decomposing numbers, we start division, and this is something I really never did when I was learning division. By the time you get to division, you're good with numbers, and you learn the algorithm, and you do it, you divide. Starting division by actually splitting things up is an incredibly, incredibly valuable activity to do. Halloween's coming up, great time to split up candy into equal groups, and then talk about remainders and things like that. But it's something not enough, I find, especially in middle school, it's something not enough kids have enough good experience doing. So when they get to word problems that involve division and splitting up anything of any kind, they don't have the instinct of, that's division. In a word problem in middle school, when a kid sees something being put on top of something else, they're adding it, and they don't have a problem with that, because we put stuff together all the time. But splitting up into even groups is an activity I'd really recommend to you as parents, with candy and just whatever you can find around the house. And young kids enjoy doing it for the most part. We also talk about related multiplication facts with division when we first talk about it. Again, composing, decomposing numbers, and number sets all being developed here. This is a snapshot from the 5th grade textbook, which again I'm trying to show you why are we spending so long on decomposing numbers, because when you're good at it you can do stuff like this. 6 times 20 is the same as 6 times 2 tens, which is the same as 6 times 2 times 10. And 6 times 20 is difficult for many kids, and the algorithm doesn't really help you a ton. It might, but it takes a while. And kids who can say, well, 6 times 2 is 12, and 12 times 10 is 120. That sort of fluidity in thinking is where we're headed with this breaking apart of numbers stuff. And we have the pictorial representation of that here as well. 27 times 30, 27 times 3 times 10, 81 times 10, 81. That's 5th grade. That's where we're headed with those. Does that look familiar to you? Yeah. So again, just a nod to, this is a lot of the stuff we see on homework, and we're saying, what on earth is this? Can you stack them on top of each other? And the answer is absolutely yes, but there's a reason for the most part that we're doing this fluidity thing to get kids comfortable. Also, our end goal in teaching all this stuff to kids is efficient and accurate answers that allow them to apply their skills. There are certain types of kids, whether they have a diagnosed learning disability or they are really, really struggling. There is a point at which going through this composing and decomposing numbers is no longer helpful and is a burden on them, and the traditional algorithm is more appropriate for them. And that, if you think that one of your kids might be in that area, especially if they're in the younger grades, I'd say let's hold off a little bit, and maybe it's getting used to it a little bit more. But we have made the decision with kids in the older grades where this kind of stuff is not doing the help it's supposed to, and they're a type of kid who we have made in a sort of accommodation to, you're going to stack them on top of each other, and you're going to multiply, and that's okay. We all turned out okay, right? For the most part. And so we have had that conversation and made that decision. If you think you might be hearing more about that, shoot me an email or talk to your teacher, and then talk to me. And for kids who are new and haven't had this before, right? That conversation sometimes is pretty quick. Yeah. Okay. Let's stack them and do it. So these are tools, great tools for math games, for asking questions, and as aids for homework. If I were to give you any tool to have at the ready when you're helping with your first grader or kindergartner with homework, it would be this right here. And I'm happy to print this out for you.
So I have a question.
Yes.
Tell me if this is off topic.
Yeah.
With the extra math.
Yes.
That seems to just be a reinforcement if they have this down.
Yes.
But I worry if my kids don't have this down, we're focusing on the extra math and we're doing this,
Mhm.
and this is getting lost.
Yes.
So I'm kind of like, what do I do?
So the extra math is because we all want efficient and
Right.
accurate. So this in combination with the extra math is a really, really good idea. There's also another app called Robin and Dob, which is a lot like extra math. You're right there. It's just for Apple stuff, iPads and phones. But it's that quick 6 plus 7. And then if you don't get it after one of 3 seconds, a little dog comes out with a question mark, and you click on him, and he holds up a 10 frame. And it's not a 10 frame, but it almost is. It's apples, and when you get 10 apples, they go and they put them in a bag that says 10 on it. It's tremendous. So it's a really good, and some of the teachers definitely know about that. We've made that accommodation for kids too, of hey, if you're still doing this, sometimes you do this enough that you get it. If that's not happening, we can switch to Robin and Dob, or we can put this on the desk with extra math. Did that answer your question?
Yes.
Good. Understanding the number system. So I'm going to breeze through a couple of these because I think I've kind of hit some of this stuff. But we do end up talking about tens and ones and stacking numbers, and that's where we're headed right now. That the number 14 is made up of 1 10 and 4 ones. And we do talk a lot about place value. And the most common number bond, once you get up into first grade and beyond, the most common number bond we make is a group of 10 and then the extras, a group of 20 and then the extras, right? That's if we think about it, probably that's the way you break up numbers mentally the most, right? Into tens and ones, because it's a very efficient and effective strategy. We just tie that to the number bond and some of the manipulatives that we use with the kids. You see activities like this that really try and reinforce that breaking up into tens and ones to manipulate numbers. And then we talk about comparing, and we talk about them in their place value. This is definitely one of those things that I took for granted. teaching this again for the first time when I started teaching, was one of those times that it blew my mind that this wasn't more clear and obvious to all kids, or most kids. 28 and 31, which one's bigger? That 8's a huge number. It's got to be the biggest, right? And when none of this stuff is present, they see an 8, and it's got to be the biggest. The fact that this one's led by 3 10s, which is already more than those 2 10s, with the manipulatives and with practice, is a very clear concept. But that's a really, really tricky one at the beginning for a lot of kids. Then we bring up place value even into the thousands. This is a lesson from 4th grade, that the 7 in the number 2,475 stands for 70, and it's all about where it is in the number of how much it's worth. And that concept's really easily reinforced with base 10 blocks. I'll show you a website here at the end too that has digital base 10s that automatically regroup when you get to more than 10. It's made by our textbook. All the stuff looks identical to what's in their text. It's a really, really good resource. I'll show you in a second. Here's a very interesting one. This is one of those things that didn't make sense to me, or at least in this way, until I taught it. 7 times 10, 9 times 10, 10 times 10, 12 times 10. The rule we learned, or at least I learned, what do you do when you multiply something by 10? Add a 0 on the end of it, right? And that's true. Until you get to decimals and everything falls apart, and we lose so many kids to decimals in 6th and 7th grade. So why do you put a 0 on it? Because what used to be in the 1s is now in the 10s, so that 0 acts like a placeholder, kind of bump everything over. With manipulatives, we really kind of stress that. And the kids still, let me tell you, take away, add a 0, add a 0, add a 0. And that's okay, because they're getting the right answer and they're doing well. But when we talk about it in the grades beyond, about why with a decimal point, what you're really doing is bumping everything over a place value. Once we've had this conversation, that conversation is a lot easier in the future. So when we do this, add a 0, and I'm telling you, the kids rock through this, and I guarantee you they tell me they're thinking, add a 0, add a 0. Remember this one too? Yeah. We do that, and that's okay, because it's getting them, but we have started the conversation about the conceptual basis. Because when you get here, if you add a 0, you get that. And if you remember from your middle school math, that's not the same thing, right? This is still 6 1s and 3 10ths and 4 hundredths. So what's really happening is you're moving the decimal point over. What used to be in the 1s is now in the 10s. What used to be in the 10ths is now in the 1s. And just moving the decimal point will get that same thing done. So we don't have to unlearn as much when we really do a good job of teaching good number sense at the beginning. Questions there? Cool. I'm going to take a sip of water. Half of my day is spent looking for the things I said. So understanding operations. We still do this, and but we hopefully understand more why it's happening when the kids get here. And when they struggle with this, we have a lot of tools to use with them. When they struggle with just the 3 plus 4, and there are kids that do, even when they're in 3rd grade, they're just not fast at it or efficient at it. We put this in front of them, see? 7. And they can get super fast at covering 3, covering 4, and seeing 3 more that aren't covered. And they know their 10s decomposition so well that they know that 7 without counting it. And on their fingers, they're counting it. So that can be a very valuable tool. Here's kind of to your point is skip counting still okay? And here it's definitely taught when you're getting to the 3s, right? And but as soon as we get beyond that, we want a more efficient strategy. So it's definitely okay still, especially if it's efficient and effective. But then we start adding with base 10 blocks, and I'll kind of skip through this a little bit because this is a little bit more traditional. Base 10 blocks have been around for I think longer than the number bind stuff. It's maybe a little bit more freedom to us, but really one thing that really lights up for some kids and some parents, definitely for me, is what was that little 1 that we were all carrying for so long in addition? It was when you added up 8 and 6, you get 14. So that 1 is 10, and that's why you toss it up there in the 10s, right? There's 4 1s that are still down there, and that website I'll show you in a second has this big whoosh sound, and it takes the 10 ones and brings them over into the 10s and makes them a nice clean 10 rod. And that's a really big light bulb that goes on for a lot of our kids. But that little tiny one is up there at the top. Counting back, a good strategy when we're doing it from 4. We tie that to the traditional algorithm and to the base 10 blocks. And we're really, again, trying to get to that traditional algorithm because it's quick and it's good. And as long as you know what the heck's going on, and we've got a place to go when you don't do it correctly, it's a really good way, and we still very much teach it. There's one other thing I want to say here. Let's see. Lost it. Here's another way with bigger numbers, breaking up numbers. I'm going to break up the 27 now in more complex numbers. And 20 and 7, where am I going to take the 4 away from? Well, those are 10s. Those are nice. We don't want to touch those. Is there enough to take away here? Yes, there is. Let's grab them. There's 3 left, 23. These are a lot of pictures that happen in the text and on the homework. And what they're meant to do is model the children's thinking. And that's a good key for you that sometimes we make the kids write this down because we can't get inside their head and prove that they're really doing the correct thinking. So we have to have them often write it down in some way. But the goal here is that this is what's happening in the kid's head. Right? Not that Singapore is trying to make everyone write this down all the time. And it goes all the way into the thousands. This is a 4th grade lesson on adding in thousands.
Can we go back?
Yep.
So why don't they think that the answer is 3?
Really good question. One thing I would do with a kid is say, first place I'd start is, don't forget about the 20. What happened to the 20? Did you do anything with it? No. If you forgot about it, make sure it stays in there. If that doesn't click, I would go to these and I would make 27 and have nice, neat 10 blocks. There's our 20. Here's our 7. Take the 4 away from those, and then how much do you have? And tie it back to the concrete. So when we're working in the abstract, we have 2 layers of places to go with kids, and that's really, part of my role in the school is to, in a smaller group, I'm able to go through those layers quicker, and I have all my manipulatives right here on the shelves and to do that kind of stuff. Where if you don't get this, I'll try and kind of trigger the lessons that we've been learning, and then give you the things to count out if you do. Does that answer your question? Here's an awesome one that's really good on that website. Again, I'll show you. I probably should just show you now. But when we're crossing out the zeros and making, I remember this is a difficult thing. Crossing out all the zeros and they all end up being 9s. What's going on there? So when we've got 2,000, I want to take away 7 in my 1s. I don't have any 1s, but there's a ton over here. So I'm going to take away 1,000, and I've got 10 now. Then I'll take away my 10 hundreds, and I've only got 9 of those, and I've got my 10s here, right? And we're marching those 10s down. And several times of doing that, then we tie to the stuff that we learned, right? But again, we have a place to go when it doesn't make sense. We're trying to get that conceptual basis on what on earth is happening when you do all those lines.
It's good to know that you're still doing the takeaway, but you're explaining it in 10s.
Yes, exactly. Because I learned that and was explicitly taught,
Yep.
cross it out and make it a 9,
Right, exactly.
right? And
So you want them to make it a
I
10
figured it out
and
after a while.
Yeah.
Yeah, I agree. You're right, you're seeing. Sorry, you're going to interrupt.
No. I mean, I think it's good just to have them do the exercise of seeing the 10 and then crossing out where first just going straight to the 9.
Agreed.
But you can still have them practice their homework that way with the whole thing?
Absolutely. Absolutely.
As long as there's some 10.
Because that's where we're all headed. And we're already in this lesson.
Right.
We've done this in class.
Yeah.
We rarely send these home, just because they are very cumbersome. But we do this in class, and then we do this in class, and we do it some more, and then we send it home. It's typically how it works.
Because my son's just doing the right hand side, which is what I know, so
Mhm.
I'm feeling like he's skipping this whole other step.
Could be, but might not be.
Okay.
And if you want to talk more about that later, I'd love to have a conversation with you about it.
Yeah, I'm just-
But the bottom line is efficient and effective. If they're here,
Mhm.
there is value, even if they can be here right away. We do force kids to do this because it's important of what it means later. But there is a bottom line type scenario of if they can do this and they really can't after a lot of practice, can't do this, this is where we want them to be, and on some level that's okay. But that's a tough decision to make I'll tell you, as a teacher, for when do you stop with the other stuff if it's really a struggle. We do that with multiplication. When you multiply by 3, what are you doing? Why do we do 3 times 2, 3 times 1? Because you're making 3 groups of 2 1s, and then 3 groups of 1 10. And there's the 3 groups of 12. And it's 36. There's no regrouping in that one, which is really nice. That's where we start. How about 15 times 5? When you make 5 groups, there's 1 group, 2 groups, 3 groups, 4 groups, 5 groups of 5, you get 25. And we can't keep a 25 in our 1s. We get to make 2 10s out of that. So that's what the little 2 hanging up there is. And then we make our, so that's where the next step. And then we make our 5 groups of 10s, plus the 2 that we regroup from over here. And that's 75. And we're hoping to get here, but we start here.
So when they're doing that in their head, like I had some kids in the car the other day, they were doing it in their head, and they were like doing multiplication, and they were grouping it. So let's say it was, just for easy numbers, 10 times 4.
Mm-hmm.
They were kind of like then doing 10 times 2. They got that number, and then they knew that they could almost add the other groups.
Yes.
Okay.
What, they're, yeah. I mean, yes.
So
they're breaking this up into
basically-
2. That's,
Yeah.
I would say, I see it, and I'm very biased. So, I think I must be full disclosure there. But I see this more often since we started doing this. In the conversations I'm able to have with a 2nd grader about the way they're thinking about a problem, by breaking this up into 2 and 2, and well, that's 20, and it's just double that, right? That's what we're trying. That's exactly what we're trying to foster. Is that ability to compose and decompose numbers.
It felt weird to me that they were like breaking it apart, dividing a portion of it, and then adding a portion
Right,
of it. And
right.
I was like,
And-
I'm like, I get what you're doing, but wow, that's like 3 steps.
And the
Really
bottom
just
line is
really
efficient and
fast.
effective.
Right?
And I'll
Yeah.
tell you, when I see them in middle school, that kid is doing this. And there's somebody else doing this. And that's not bad. That's the way I did it until but this is what we're trying to foster as much as we can. And we're not just leaving it to the kids who figure it out and the kids who don't, and the kids who like it and the kids who don't. We're explicitly teaching it. And that feels weird sometimes, and it gets hairy sometimes when you're explicitly teaching stuff that makes us go, wait, what?
Well, we were at the car, and I was like, I was doing the car.
You're checking it for them? Yeah. It's agreed. So, here's my quick thing on the division algorithm. If you're a math person and you enjoyed math when you were going through school, and a lot of this is really making sense to you, and you could explain what that little 1 is when you were carrying 1s, or where all the 9s came from when you crossed them out with all the 0s. That was me, and I am maybe ashamed to say, I don't know. I learned what the division algorithm was when I came to Good Shepherd and started teaching division. It tries to make sense of the division algorithm. Because the division algorithm I learned was multiplication, subtraction, and bringing down numbers with arrows, right? Which, no wonder kids don't know that division, or forget at some point along the line that division is about splitting up into groups, because it's not. It's about how many times this goes into this, and subtracting, and, right? So this is a quick on what the division algorithm is. My disclaimer here is, we are having a conversation at Good Shepherd now about, this is really, really hard for kids. And we have made the call in the past for some years of students that the traditional algorithm is the only way that they're able to get an efficient and effective answer, so that's what we're doing. We've had the conversation and made it of, that's what's happening. And it's kind of an ongoing conversation here. So you know, this is the one I'm still not sure about. I'm very, I will defend a lot of the addition and decomposing numbers. This one's tough. So here we go. 63 divided by 3. What we're doing is we start backwards, A. It's the only thing we start in the, at the highest place we can. So we're dividing 60 into 3 equal groups. And there it is. How many go in each group? 20 go in each group. So I put the 2 in the 10s. How many did I use to group? How many did I successfully split up into groups on that step? 3 groups of 20 or 60. So now, of the original 63, I only have 3 left to regroup. Sorry. So there's the 3 that I have left to regroup. Now I'm going to take those 3 and split them into 3 equal groups. How many go in each group? Only 1. So the 1 goes into 1s. How many did I successfully group up on that step? I grouped up 3 on that step. And I only had 3 to regroup, so I'm done. No remainder. I successfully grouped them all. That's what the traditional division algorithm is. That's what we were all doing, which is my big light bulb. It is, as I can see from many of you, it took me many times going through it. When you get into the thousands and you see all these zeros, it really makes bringing down difficult, because the kid will bring down the hundreds when they're just, all the way down to the ones when they're the hundreds. It's hairy. It's been really successful for some kids and not for others. So it's something, honestly, we've pulled the plug on at times and said, this isn't what it's supposed to be. Efficient and effective and knowledge building and beneficial for the future. So we're going back to the old school. Questions on that? Sorry about that, I had to toss it. Yeah.
What grade are you kind of making?
4th grade.
Okay.
4th grade. 3rd grade is, because I'll tell you, with this specific example, 63 divided by 2, when there's no remainders and it's a 2-digit number, doing it with the place value charts is incredibly. There are kids within 10 minutes that can do division problems like this with the place value charts quickly and effectively. But so it's not this that we're worried about really in 3rd grade. They can all get, but then tying it to this, there's a big disconnect there. I guess thank you for asking that, because I can make that more clear for you now. They can do this scary well in minutes. And then bridging the gap over to this is really hard. When we're doing addition, they can see how this connects to the stacking on top and the 1. They get that, and this is really hard.
They starting to do sums in 7th grade?
You think? No, division should be all. The slide with the 42 divided by 6,
Yep.
that was 2nd grade. And the algorithm, long division algorithm, is 3rd grade. And then remainders, 3-digit numbers, 4-digit numbers in thousands, that's 4th. This is something that would show up on homework then. So when you're doing this kind of, this would be a halfway step to the traditional algorithm. When you're doing 48, first divide the 10s. 48, 4 10s divided by 2 is 2 10s. And then divide the 1s. 8 1s divided by 2 1s. But divided by 2 is 4 1s. So I've got my 2 10s and my 4 1s, and it's 24. All right. I'm gonna skip through the division here because I feel like we've at least touched on that adequately. Yeah, we don't all are all good. So this is what I just jumped the gun on telling you. Why for the division? I'll defend it for addition and subtraction, multiplication all day long. Why for division? For the reasons we've explained, but it's really hard. It's really hard. So, mental math. 10 minutes left. Any other questions before I jump into mental math? Okay, so a word on mental math. One of my favorite parts about this program is that we teach mental math, because it's the biggest discrepancy I see in kids in the older grades, kids who are able and kids who are not able. And because we never teach it, that makes a lot of sense. There are kids who are good at math and like math and figure it out, and there are kids who don't and don't. So explicitly teaching it is incredibly important. I think it's really valuable, and doing it well means that the kids like it, and it can be really valuable. But it's hard. to teach a kid what to do in their head is difficult, with the extent that I'm going to show you here in a second. It's also really weird because when we send mental math home for homework, what do? How do you prove a kid's done it? How do you make sure that they're doing it correctly, right? It's really difficult. So at some point in teaching mental math, we show them on the board how it's done. And we make them write how it's done, which is all really weird because it's all supposed to be happening in your head. But it's kind of a necessary evil to the mental math. So 58 plus 8. Does anybody want to be brave and shout out the answer and maybe how you know?
66.
Sweet. Well, how'd you know?
Because you just,
Because you just know.
close to 10.
Right? Yeah.
And you just add 10 and subtract 2.
Did you see this happen? So this is a great strategy. Some of you might have said, I took 2 to close it off to 60 and then 6 more, right? And we foster that and build that in Singapore math. Here's another strategy, and that's add 10 and then take 2 away. I love 10. I love adding 10. I can add 10. Your kids can add 10 to anything. 58 plus 10 is 68, and the 2 I wasn't supposed to add makes it 66. So we end up, this is what we see on homework, right? And it's ridiculous, but it's unnecessarily ridiculous to foster what's going on in your head. So anybody want to take a stab at it? You want to do it your way on here, maybe? 58 plus 8 would be?
Is 10 minus.
58, so I'll sorry.
I don't know. I don't know what you want me to
I'm putting you way too on the spot.
Okay.
58 times plus 10, and then 68 minus 2 is 66. Here, just again, it's really great with 9s. It's even more clear. We usually start with 9s, right? Because you only have to take 1 away at the end. It's a lot easier to jump mentally to just toss 10 on and take 1 back. And that kind of language is really, really great with kids. You know, give them 10 and then take 1 back. That's a lot of things we say. And then hope you can see at this point, I don't even have to build 76. If I say you have 76 and now I give you 10 and you've got 86 and now I'm going to take 1 back, right? One of those 10 bars, since we work so much in 10s, it was a really great thing to have. Anybody want to take a stab at this one? How you might do this in your head? So what I would hear a lot from parents, and my instincts were to say with kids is, you just add the 3 and the 6, and then it's 9, and then so it's 259. And some kids will go, awesome, great, and some kids will say, what? So I wanted to show you this because we tie it to the number bot, which is something that they've seen every day and are really familiar with. And this now is a vehicle by which we have the conversation of, I'm going to break that 253 up into 253. And because I'm on the 10s here, I'm going to give the 6 here and make 9 and 259. It's not the most complex concept in the world, but we're tying it to something that they're really, really familiar with. Because some kids really don't understand why it's okay to just give it to the 3. It shows that they don't have a really great understanding of place value. They really don't see that as the 1s and the 1s. If they do, then they're able to do it, and if they don't, this is a really good bridge to help them. So we might see something like this. All right. Here's another great one for adding 4, but I wanted to show you that sometimes we stretch it a little bit too far. If you're adding 4, I'd count up, or add 2 and 2 to do that one. Adding 10 and then taking away 6 when you're just doing 4 seems a little bit much for me, but it's good stretch thinking, I guess. And ultimately, we're looking for that efficient and effective answer. And here's where it really, really can get valuable. 345 plus 80. And the exact same strategy can be used here. I'm just going to add 100, 445, and take away 20, 425. That's something that's a big jump. I would see most kids, and a lot of adults will write that down, right? Or try and do the traditional algorithm in your head and carry numbers, and that's really hard. I don't know if we have a lot of people who are really, we're really strong in school and math, but doing the traditional carrying mentally is incredibly difficult. It's incredibly difficult. And these strategies, when you're more fluid with decomposing and composing, can be a lot. Adding 100, taking back 10. Am I going too fast in this mental math, or is this good to do? All right, here, when you're doing 469 plus 200, we're going to break it into 469, add the 200 to the 400, 600, and then toss the 69 back in. Again, just using the number bond as a common language and a bridge to what we're doing. Let's see here. Yes. This is a great one. 63 minus 48. There are very few people I know who would try and do that in their head without a good mental strategy. But now, especially with subtraction, it's really, I use this now. 63 minus 50 is 13. But I wasn't supposed to take away 50. I was only supposed to take away 48. So I'm going to toss 2 back out. It's 15. I don't have to regroup in my head. I'm using my knowledge of numbers, my number sense, to do that. Same thing here. Take away 50, give 3 back.
How about adding, what I would do, take 47 to 50?
Yes.
And then, I mean, is that kind of the same, I mean, it's the
Absolutely.
same concept, but
Absolutely. No, I think
rounding
that's what
up.
I think that's what they're doing.
Right.
Yeah,
Okay.
definitely. No, definitely. That's right on. That's right on. Mental math for multiplication. This is a really strong one. A really, really good strategy. 7 times 6. This is where I feel like I really see some value of Singapore, because I memorize my times tables, and I memorize my times tables, and that's how I did it. 7 times 6. If a kid doesn't know an efficient and effective strategy to get there, that's not just back of the pile, I'll tell you again, can be really, really good. And here's what we do. Now that we understand that multiplication is groups, 7 times 6 is 7 groups of 6. So when a kid's trying to figure this out, 9 times out of 10 they go 6, 12, 18, 23, 20, right? And then it all falls apart. But most kids can tell you very quickly what 5 times 6 is. 5 times 6 is 30. So we're super quick. We teach in Singapore 2s, 5s, and 10s first, because they can do them automatically for the most part. And then we fill in all the other numbers that are difficult to skip. So they know that this is 30. So encouraging the kid, start at 30. 36, 42. Right? We're adding 6 on top of, this is 5 times 6, it's 30. 7 times 6 is 2 more groups of 6. And there's the extra. Some kids will say, 36, 42. Some kids are honestly really glom onto this strategy and are really good at decomposing numbers, and they go 30, 12, 42. An awesome one to hear by the time they hit, 3rd, 4th grade, 5th grade. And it's written out this way. 7 times 6 is equal to, or is the same as, 5 groups of 6 plus 2 groups of 6, which is 30 plus 12, which is 42. Another great tool. If anybody wants one of these, I'll make you one. Is this guy. This is your, part of the reason multiplication is tough is because it's a lot to count out, but these are pretty quick. This is your 4's times tables in manipulative form. This is 2 groups of 4, 3 groups of 4, 4 groups of 4, okay? So when I do 4 times 7, well, what's 5 times 7? And then what's 2 more? And the act of revealing those and moving them past is a really, really good trigger for kids. I've had the most success teaching this strategy to kids who are really struggling with these things, because it's efficient and quick, right? And it really drives home the revealing of the groups which we're trying to foster.
Can I
So,
ask this?
yes.
So why isn't that in groups of 5s? If you say like 5s and 10s are the numbers they learn, so why are you doing that in 4s?
Because it's the hard one.
Oh,
Because 5s and 10s, we don't.
They automatically.
I don't even think they exist, honestly. Look, I've got 3s, 4s, and 6s here.
Okay.
Because they don't. Again, since we're all trying to get to that efficient way, they're good at 5s. We don't need it. And there are kids who do, but those maybe are the kids. Yeah.
Got it.
Great question. This is a really good one as well. I know the 9s trick. Teachers still teach that. Parents still. I still love when kids come. I have 3 kids a week come run into the room and show me the 9s trick with their fingers for how to do it, and I love it. It's efficient. It's effective. It's great. Right? They get to and they love it. Another way to multiply by 9s is to use this strategy of, that's 9 groups of 6. Well, 10 times 6, 10 groups of 6 is 60. And 9 groups is 1 less group of 6. So it's 54. And that's what we're showing. That's 60, and then take away 1, which on this would be putting it back in the units. And here's where we're headed in 6th grade and beyond. 6 times 13 is the same as, I had this conversation with my algebra students. 6 times 13 is the same as 6 times 10 plus 6 times 3, which is 60 and 1870. And this is a lot easier conversation to have a kid who is a possible conversation to have with a kid who has strong number sense, because they understand decomposing numbers and more than just the traditional algebra. So here are your top phrases, and I might even be done on time. Wow. Number 1, let's look in the book. Like I said at the beginning, unless you want to be, if you want to be, I'll make you a Singapore expert. We can have coffee together every other week, and we can do it. But we don't need you to be. And we know you guys are busy, and thank you again for coming tonight. But let's look in the book is a really good and okay thing to say, to trigger you and to trigger them. Oftentimes kids open up the book and they're starting to bring themselves back to class and see. I have digital, a link to the digital resource of the textbook that I'll show you. Show me with your 10 frame. If you have a kid who's struggling on something that's making you, as an adult who knows these things, go, what do you mean? What do you mean? What's 10 plus 4? Yes. Can you show me? Show me what 10 plus 4 is. Give them something to count. With many kids, it's hilarious and amazing how efficient they can be by doing 10 and 4 and covering it up with their hands. Sometimes they don't need counters, and it's a lot more efficient than stuff you can stack and play with. So just having one of those at the ready. Can you show me? Can you show me on your 10 frame? Or even just show me. Using place value language of 1s, 10s, and 100s. Hopefully you've seen that when we're doing the traditional algorithm, that's the language we're using. And it's okay to say borrow, and it's okay to say carry the 1. But it's also okay to say, how many 10s, how many 100s, how many 1s. That place value language, they're getting a lot here. This is not meant to be cruel, but is one of the things I say the most often with my students, and that is, are you sure? From a very early age, I realized in myself that I was teaching kids, if I asked them if they were sure, it meant they were wrong. And the only time they ever thought they were wrong is when I asked them to push their thinking. And in this program, all I'm doing is asking them to push their thinking, right? And if we only ask our kids if they're sure when they're wrong, what they translate, are you sure, into you're wrong, try something else. I've had kids stare me in the face in 6th grade and tell me 2 plus 2 is not 4 if I say, are you sure about that? Because they're only asked to, are you sure, when they're wrong. So asking, are you sure, and prove it is another great one. Show me, prove it. And with the younger kids, they think it's hilarious, and it's kind of fun, because they like showing what they know. And when they're really confident in it, they love showing what they know. 5 plus 7 is 12. Prove it. Prove it. Use a 10 frame. Prove it. Tell me your thinking. Getting in, if you're feeling more comfortable with some of these things, asking the kid what on earth is going on in their head. What are you thinking? Can be a valuable insight into what they're doing. And sometimes they hear themselves start to explain something and redirect and recorrect themselves. Tell me your thinking is really great. And here's the last one that I'll say again. That's enough for tonight. Is an okay thing to say. I don't think anybody is going to be doing this to the extent that it's going to become a problem. With that, if you are, we'll talk to you. But it's not going to happen, right? Because we all want the same thing. And if the kid's not independent yet, then we want to know that. Then we want to know that. So I promise I've had that conversation with people, and we're on the same team. So if it's not happening tonight, it's not happening tonight. And then a quick note on the homework is really valuable. Because there are kids that come in and say, I couldn't do it, and there's no note from you, and that can be. We have wonderful children here, but that's not that happens, right? Oh yeah, I didn't get it. So a little note or from you, or an email to the teacher would be really helpful if you can. And that's it.